Millions of passengers pass through U.S. airports every day, and each one of them has to pass through a familiar screening checkpoint to ensure that nothing on their person or in their belongings poses a threat to aviation security. Alert has been tasked by the DHS Screening at Speed program to develop CLASP with the goal of enabling the smart checkpoint of the future, one that knows exactly where all the passengers and their belongings are at every point in time, and then use this information to assess flow rates, detect thefts, left behind items, and enable risk-based screening. The Costas Research Institute at Northeastern University was the perfect environment to develop CLASP. It's a secure, access-controlled facility that allowed university researchers to develop algorithms and conduct experiments in a space much larger than a typical academic research lab. In 2016, the CLASP team began working on a testbed at Costas with the goal of creating a highly accurate version of an airport security checkpoint. Working with the TSA and their vendors and alert industrial partners like Smiths and Rapiscan, we instrumented the testbed with equipment such as an X-ray luggage scanner, a walk-through metal detector, a device that you would use in secondary screening, pretty much all of the same equipment that you would see in an actual airport security checkpoint. Here we can easily run controlled scenarios with groups of actors to simulate a busy day at the checkpoint, including passengers in wheelchairs, families and their children, and even thieves on the lookout for an unattended cell phone or laptop. All of this activity is captured by a custom-built network of 22 security cameras mounted on the ceilings and the walls, and connected to a powerful computer and a network video recorder. Since we have opened the space, we've collected 26 synchronized video recordings involving dozens of passenger and TSO actors. One event even included a service dog.
The first part of the problem is to detect and track all of the passengers going through the checkpoint. While passengers generally move in a straight line from the divestment area through the millimeter wave machine to the back pickup area, many things can happen along the way. A passenger may forget to put their keys and wallet onto the conveyor belt, be pulled aside for secondary inspection, or have to corral their excited children. We find that it's generally easier to track passengers from the cameras in the ceiling looking straight down, since they can be better separated from each other. Our current passenger tracking solution uses a deep learning algorithm trained on many examples of what passengers look like from above. Since each camera only has a narrow field of view of the checkpoint, we need to use the known positions of the cameras to be able to match passengers as they leave one field of view and enter another. Our algorithms are effective even when passengers are temporarily hidden from view, such as when they pass through the millimeter wave machine or are not fully visible in any of the cameras. We also track the TSOs, the Transportation Security Officers, that are on the other side of the conveyor belt or that are assisting with secondary screening.
The next step is to track all of the belongings a passenger may place on a conveyor belt for screening. Currently, we assume that each item or group of items is placed in a standard issue bin. We have to keep track of each bin, whether it's empty or full, from the moment it's placed on the divestment table to the moment it's picked up by a passenger on the other end. While bins generally come out in the same order that they come in, there can be a fair amount of bin shuffling as passengers try to quickly divest their items, and TSOs may select certain bins to rescreen, changing their order. The bins are also hidden from view for quite a while as they go through the X-ray scanner. Similar to the person tracking, we use a custom-trained deep learning model to detect and track each bin. It's especially important to know whether a bin has been completely emptied at the end of the passenger pickup area to be able to flag left behind items.
So then we need to put together the track people and bins to keep accurate track of what bins belongs to each passenger. Understanding when a bin belongs to a passenger turns out to be a really hard problem, since many hands may touch the same bin on its journey, for example, just to move it along the rollers. We train an algorithm that's able to accurately determine when a passenger is putting items into or removing items from a bin, and can distinguish this from just touching or moving the bin. We can use the same algorithm to also classify other passengers' actions and interactions at the checkpoint. For example, a passenger giving an item to another person or somebody pushing a passenger in a wheelchair. Maintaining accurate bin ownership is critical so we know whether passengers have picked up all their belongings or when another passenger is actually stealing an item from a bin that doesn't belong to them. For example, you can see in the video that we're showing our algorithm detecting a theft event when passenger 1 steals an item from a bin that belongs to passenger 2.
We take all the results from the passenger tracking, bin tracking, and association algorithms to create a holistic, bird's-eye visualization of the checkpoint. We can tune this news feed to show every small event happening at the checkpoint, or filter the results to only show important events such as left behind or stolen items. Combining all the results lets us make accurate measurements that are important to keep the checkpoint running smoothly, such as the average length of time a passenger takes to get through the checkpoint, the average time they are separated from their belongings, or the volume of passengers and bins passing through the checkpoint at any point in time.